Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn how to perform unsupervised learning in natural language processing. For this particular tutorial, we will learn topic modeling, which is the problem of, so you have a body of text, and based on the words in that text, being able to come up with topics contained in that text in an unsupervised way. So our predictive model, we are not going to give it labels. This is not a supervised learning problem where you give the features and the labels. We're only giving the features, which is broadly speaking the words in that text, and then the model will learn by itself to generate topics based on that text, on those words. So pretty amazing. So the technique that we are going to use is called latent Dirichlet allocation, or LDA. And LDA is used to classify text in a document to a particular topic. It builds a topic per document model and words per topic model, and this is modeled as Dirichlet distributions. So, and you'll see how this works as we go along. So let's go ahead and go to the first step here. So we're going to load our data set. So this is the data set that we start off with here. This is a part of the CSV file. So we have news, ABC News from 2003, so for a 15-year period. And so we have the published date, and we have a headline text. Those are two columns here. And as you can see, they're just headlines text for headlines for news, for the ABC News. And we want to create a model, a predictive model that is able to learn from all of the words that appear in this whole body of text, of thousands and thousands of entries, and come up with topics by grouping these words together by itself. Pretty amazing. We'll see how that works. So first, let's import pandas as PD, and now we're going to read CSV. So let's create a data variable here and assign it to pd.readCSV, and let's just load in our CSV file, which we have in our local directory. And here, so here we only need the headlines text column from the data. We really don't need to learn the date here. We just need the headline text for this example. So and we're only going to grab 300,000 entries here from the data. So from our data, let's start from the beginning to 300,000. So let's grab those entries, and then we only want the headline text here. And now we're going to go ahead and add another column called index, and we're just going to assign it to our data text.index. It's a member in our data text, so where we can grab the index of each entry. And now, so let's go ahead and print the length of the document. So it's 300,000. Good. It's just a sanity check. And let's go ahead and also display the first 5 entries in our new data set here. So as you can see, in a pandas data frame, this is by default. But here we have our headline text. We no longer have the date. That's good. And then we have our index. And you'll see in a moment why we want the index by itself here. And if you'll notice that this text is already in lowercase, punctuation is removed, and so on. But we still want to do some data pre-processing. So we're loading the data. And now we're going to pre-process that data, because we can't just feed it directly like that into our model. We actually want to do some transformations first. So natural language processing, these are some very standard data pre-processing steps that we do. So the first one of them is tokenization. And this is the process of splitting the text into sentences and the sentences into words. And lowercase, the words are transformed to lowercase, and the punctuation is removed. I mean, why do you want to convert to lowercase? Because we don't want to have 2 different words, and the only difference is the case, lowercase or uppercase, because that doesn't convey any meaning. That doesn't change the meaning of the word in terms of our model learning those features. So we don't want that to have an effect. So we just lowercase that. And we also remove punctuation, because again, we don't want to look at commas and periods and things like that to extract meaning. We're doing topic modeling, so we want to look at just words and come up with topics encapsulating those that contain those words essentially. So we're also going to remove words that have less than 3 characters. We're going to assume that those are not important to convey meaning. And also all stop words will be removed. Now in NLP, stop words are words that, again, don't really convey any meaning for the task that we want to do. So for example, the THE in English would be a stop word, because it just doesn't convey any meaning. It doesn't help us learn what are the topics, for example, in a given document. So we want to remove those stop words. And libraries have a built-in collections of stop words for different languages. And so words, we also want to lematize words. And lematize means it's just transforming words, for example, that are in third person, change them to first person. And for example, verbs that are in past and future tenses, we want to change them into present tense. Again, why do we want to do this? Is because, for example, if we have two words like reading, read, those essentially convey the same idea, which is reading, right? The act of read, so that the meaning of the word, the core meaning of the word, is the same across these different words. And we want to convert all of these words to be just essentially one type of word. We want to lematize it in the same tense to remove the quote unquote duplicate words that we have, and to reduce the number of learnable parameters for our model, and just make it simpler and faster to train our model. And also, words are stemmed, so in addition to lemmatizing, we also want to stem words, and that means to reduce them to the root form. And if each word has a root form, and a lot of libraries automatically calculate that or get that root form for you when you use those methods or functions. But again, we want to just keep it as simple and pre-process this text, because we only want to be left over. We want to have left the core words that convey core meaning about this text. So this is okay. We're not really losing valuable information here in our case for topic modeling. So here we want to load GenSim and Natural Language Toolkit library. So NLTK is very standard in NLP for processing text and so for dealing with text and machine learning. Now, GenSim is a production-ready open source machine learning library for unsupervised topic modeling and natural language processing. So it's perfect for what we want to accomplish here. And as you'll see, it's going to be very helpful for some of the machine learning, some of the tasks that we're going to do with this text. So if you don't have it, just install it here, pip install. For example, here you can do that. So let's go ahead and import it, and to some of these other imports here, we want to import this simple preprocess that is essentially going to tokenize our sentences in our document, and so on. Also going to import stop words from gensim.parsing.preprocessing, and from nltk.stem we want to import wordnet lematizer and snowball stemmer. So again, these are just functions that we want to use, or objects that we want to use for lemmatizing and stemming, as we discussed already. And let's import NumPy as well. So, and by the way, at any given time, feel free to pause and just do it at your own pace. Make sure you understand what's going on here. So we just import NLTK, and then let's go ahead with start with lemmatize here, an example of lemmatizer example. So let's go ahead and grab a word. We just call it went. It's a word that is went, right? The past tense of go. So we're going to go ahead and create an object, wordnet lematizer. Just call the constructor here. And then let's call the lematize method on the word lematizer object here that we imported. And for two parameters here that we're setting for this example, let's just pass in the word that we want to lematize. And let's pass in what it is, an adjective, a verb, and noun, in this case V for verb, because it's a verb, went. And see, when we print it, we get the word go. So again, what does lematize do? Words in third person are changed to first person, and verbs in past and future tenses are changed into present. So we have a past tense word, and we convert it into its present tense. And that's going to, once we do it for the whole text, that's going to, every instance, every variation of the word go in different tenses is going to be converted to go. And we only have to look at that word and learn, and as far as our model. So it's going to make it a lot simpler and faster. And so that's a lemmatizer example. Let's look at a stemmer example. So stemming, again, the process of reducing words to the root form. So let's create an instance of our snowball lematizer here that we imported from nltk.stem. And let's just pass English, because that's the particular language that we want. Libraries have different variations for different languages. And as an example, let's create a list here called original words, and let's just put in some words here, arbitrary words. And let's go ahead and now create a singles variable. And let's assign it to a list comprehension. So for each word in this list, we call it plural. So for plural in original words, we want to call our stemmer object, we want to call the stem method on this object and pass in each one of these words. And it's going to stem it and reduce each one of these words to the root form. So let's go ahead and create a data frame to display. So pt.data frame, and let's just pass for the data parameter here. Let's just assign our dictionary here, which is the original word, so the name of the column, and then the actual data here, and also the stem. So we see the difference, what happened. So we have caresses first, and then the stem word is caress. It's reduced to its root form. And see some of these words sometimes don't make sense logically. Like for example, humbled, the root word happens to be humble without the e at the end, and this just depends on how libraries are written and optimized to stem words, but still the core meaning of the words is still retained and just makes training and dealing with the data a lot simpler. So two-step, lemmatize, and stem the words. And of course, we'll also do tokenization. So we'll see how that works. And let's actually write two functions here to perform these pre-processing steps when we do it on the entire data set. So first, lemmatize stemming here. So we're going to do lemmatization and stemming in one step, taking in a text here as a parameter. So we have our wordnet lemmatizer as before, and then call the lemmatize method on it, pass in the text, and then we're going to put the return of that, so that the value that comes out of that inside as a parameter for stemmer.stem method. So to just do it in one line, just go ahead and return that. So it's going to lemmatize and stem and just return that. Now we have another function here called preprocess, and that's going to do the whole thing. So tokenize, lemmatize, and stem. So we're going to pass in our text here as our parameter, and let's create so let's do a for loop here. So let's create an empty list result. So for token and gensym.utils.simple preprocess. So this simple preprocess is doing a tokenization, right? Which is grabbing our sentences and tokenizing and splitting it into words. So we pass in our text here. And so for each token, so for each tokenized word in the text, so if that word is not in gensym.parsing preprocessing stop words, so if it's not in the stop words, in that collection of words, remember stop words are words that don't matter for meaning, like the, for example, in English. So if it's not one of those words, and the length of that token is greater than 3, then that's how we say, okay, this is a relevant word. Then we want to append that to our results here. So result.append and lemmatize stemming. So we call this function that we just created and pass in our token here, and then we loop through all of them, through all of our text and all of our tokens rather in our text, and just return that list. And that's our pre-processed data, which is very nice. So let's go ahead and look at an example here. So let's just preview a document after pre-processing. So let's just grab this 4,310, so document number, just arbitrarily, just to see how it's working. And let's create a variable here called doc_sample. Let's assign it to our documents that we created before. So here, so we have our documents, which is this data right here. And let's go ahead and access. So let's do a Boolean check here. So for index, if the index happens to be the document num that we define here, then we want to grab the values from there. Now this basically converts it to a NumPy array. So we want to grab, the structure looks kind of like a matrix type of structure, so like nested list. So we just do 0 and 0 to grab the value inside of it. So here we print the original document here. So for word and doc sample, so we're splitting at the white space. So we have the individual words, then we append them here. You can also do this in one step in a list comprehension. So let's go ahead and print the original document, so the words. So we have rain helps dampen bushfires. And then once we actually pre-process, so now we're going to print the pre-process function having passed in the doc sample as a parameter. So here, so rain still is the same, helps is reduced to help. Okay, dampen stays the same, and bushfires is to bush fear. It just happens to, that's how the transformation ends up being. And let's actually display the documents here. So now we're going to actually pre-process all of it. So this was just a particular sample from the data, but we want to now transform all of our data. So to do this, we're going to use a map function. So we have our documents data frame. This is a pandas data frame here. So we actually just want to grab the headline text here for this transformation. This is the only thing that we want to transform right now as far as text, right? We want to grab that now. Once we actually grab the headline text, right here, this object is no longer a data frame. It's actually a pandas series, and series, a pandas series have a map method there. So we're gonna the map function. So we're gonna call map on this series headline text, this column, and we're just going to pass the function this preprocess function right here that we used before, and we basically what we want to do is we want to apply that function to every entry there in that series, to every element in that series, and it's going to transform each one of these sentences. Okay, so we have that, and now let's actually preview some of them. So preprocess docs, let's grab until just grab 10 entries, and as you can see, they're lists, and they have been stemmed, lemmatized, and tokenized. And you don't see stop words either. So only important, relevant words are left over. So now we're getting closer to having the data in the way that we want it. So now the next step actually is we want to do a bag of words on our data set, which means, for this topic modeling, we want to want a model that looks at these words, and based on the frequency of the words in the text is going to come up with topics. So we want to keep track of these words and also the frequency, so the count, so how many times those words appear in this data set, in these documents. That's going to be important for us to determine the topics. So let's actually go ahead and create a dictionary here for gensim.corpora.dictionary. It's just a special dictionary here for this NLP task. And let's assign it to a variable just called dictionary. And our goal, what we want is we want a dictionary containing the number of times a word appears in the training set. And now we're going to pass our process docs here that we have before. So we have our dictionary object here, and let's just check our dictionary, what it looks like, the one that we just created. So for KV, so for key value in dictionary.iterItems, again, this is a special purpose dictionary here in NLP. We want to print the key and the value, and we just want to break after it's 10. We just want to display 10, not all of them. So as you can see here, we have broadcast, community. We have all these transformed words, and each one has a particular key here. So let's look at our words here. So we have, these are the first 1, 2, 3, 4 words, and as you can see, they're printed, but they're printed in an alphabetical order. So let's actually take a look here. So the next step. So once we have our dictionary here, the next step is to filter out some extremes, like some. So we want to filter out words that are very rare and very common. That's also going to make training easier and go faster, and help us understand what's going on. So words that are appearing less than 5 times, we just want to remove them. They're not common. We assume they're not significant. And as you can see already, there's hyperparameters that we're already setting in a way as part of this whole task. So for our dictionary, we call filter extremes method on our dictionary object. And let's set these 3 parameters. So no below, we set it to 5. So again, words appearing less than 5 times, we don't want them. And words appearing more than 50% of all of them, of all of the entries, we don't want them as well, of all the documents. And we want to keep 100,000. Now, so the next step now, we actually want to convert our document, which is a list of words, into a bag of words format, which is a list of tuples with 2 elements. So it's the token ID and the token count. So we want a token ID that we have here from our dictionary, but we also want, which is an identifier for that word, and we also want the token count, so how many times it appears here in our data. So each word is assumed to be tokenized and normalized, and we don't need to do further pre-processing here. So let's go ahead and create a variable here called bo_corpus, stands for bag of words, corpus of words, and it's going to be assigned to a list comprehension. So for document and process docs, so for each each one of these entries, each one of those elements in our process documents. We want to grab the document and we want to call dictionary object called document to bag of words. So it's a very nice method that we have here in our special dictionary object, and we just pass in that document, and it's automatically going to transform it from its document format, which is this format, a list of transformed words, into a bag of words format, which again is a list of tuples. So it's that ID, that integer identifier for that word, and then the frequency with which it appears in that entry. So in this example, in this case here, for the document number that we used before of 4,310, we see it's, so these words, each one only appears once. So that's why here we see 1 for each one, and then its associated ID integer. So we have that, our bag of word corpus, and we can just access it direct like this, just by index. Now let's go ahead and preview our bag of words for sample preprocess document. So for that particular index, let's go ahead and print some information here. So we have the bag of words doc, right? This variable that we created here at the ith, so it starts at 0, 1, 2, 3. So it's going to loop for I in the range of the length. So the length we know it's 4, so it's going to go from 0, 1, 2, and 3. And we just print some data here, and as you can see, so for word 76, for identifier 76, which is the word bush fair after transformation, appears 1 time, and so on. So we have that. Now the next step that we can do is to perform TFIDF, which stands for term frequency inverse document frequency. So this is basically a method and it's a standard procedure for latent dirichlet allocation, LDA, when using a bag of words model. So essentially what we want to do is, it's a way to score the importance of words or terms in a document based on how frequently they appear across multiple documents. So for example, TF stands for, so it's the number of times a term appears in the document divided by the total number of terms in the document. So for example, if a word appears frequently in a document, we assume it's important. So we give that word a high score or a high weight. Now, if a word appears in many documents, we assume that it's not unique. It's not unique. Therefore, we give it a low score. So we're basically weighting the words based on 2 factors, on how many times it appears in the document and across all of them, and then its frequency relative to the whole to all of the document. So again, TF, number of times the term appears in the document, divided by the total number of terms in the document. And then IDF is just a logarithmic function here of a function of the total number of documents divided by the number of documents with the term W in it. So it's just basically we're assigning weights to each word based on the term frequency and inverse document frequency. And as an example here, so consider a document containing 100 words where the word tiger appears 3 times. So the term frequency for tiger is 3 divided by 100, so 0.03. Now, assume we have 10 million documents and the word tiger appears in 1,000 of these. Then the inverse document frequency, the IDF part, is the log of 10 million divided by 1,000, which is 4. So the TF-IDF weight is just a product of these quantities. So let's go ahead and from Gensiv, let's import corpora and models, because we're going to use some methods here. So let's actually create a TF-IDF instance here. So we're going to grab models.tfidf model, and we're going to pass our bag of words corpus that we had before. Again, it's the identifier, and each word has an identifier and the frequency in which it appears. And now we want to actually also apply a transformation on it. So we have our corpus TF-IDF, and we're just going to assign the variable, and then we assign that to TF-IDF, and we just pass our bag of word corpus. So, and here I just printed it for 1. We just printed for 1 arbitrarily. So we have the index 4, 5, 6, and then that is the weight, the actual weight associated with with those words based on what we discussed here. And feel free to pause and see how TFDF, how term frequency, inverse document frequency, weighting works. But here, each word has a weight based on its appearance on the entire document, on the entire data set. Yeah, and here we just print it out. And now we want to run LDA using bag of words. So this is the part where now we're going to actually create our model, and our model is going to learn the topics. Finally, getting to the unsupervised learning part of it, our model is ready. So we have several hyperparameters here, and some of them are the number of topics. So it's the number of requested latent topics to be extracted from the training corpus. So I mean, it's unsupervised learning, so you can, it's the number of topics that you want out of it for this topic modeling problem is arbitrary. You can say 10. You can change that number, and here you can see it in code. And index to words also, it's a mapping. It's also from IDs to words, and it's integers to strings, and it's used to determine the vocabulary size. And it's also used for debugging and topic printing. And this is just a worker, so it's the number of extra processes to use for parallelization. And we use all available cores by default. And here we're only running on CPU. We're using all CPU cores. And alpha and eta, there's hyperparameters that affect the sparsity in the document and topic word distribution. So just, again, feel free to pause and just see on your own just some of these parameters that you can set. But here we're going to create an instance of an LDA multi-core model. So latent directly allocation, multi-core, from gensim.models, and we assign it to an LDA model variable, and we pass in our bag of words corpus, the number of topics that we want output from our model, and then our dictionary here that we created. Passes, the passes stands for epochs here, and then the number of workers. So we just want 2. So for example, passes the number of training passes through the corpus. So if the training corpus has 50,000 documents, chunk size is 10,000, passes is 2. Then this is how the training is done in 10 updates. So chunk size here, you can think of it as representing batch size. So now for each topic, let's explore the words occurring in that topic. So this is we have our model here, and when we created it learned, basically went through all these passes and it learned. And now let's actually go ahead and output the topic. So for index topic and LDA model.print topics, so there's a print topics method in our trained object, and we just want to go ahead and print out the index and the topic. So it doesn't tell you the name of a topic, it just tells you there are these topics. In this case, we asked for 10, so we got 10 topics back here, and we're printing all of them. And the model is telling us what are the words, the important words that appeared for that particular topic, for topic 0, for topic 1, and so on. These are the words with the relative weights here. And again, and on unsupervised learning, sometimes it's not clear what the results are from our model. You also have to use, as humans, we have to use intuition and look at our results and ourselves try to make sense of the data. But some of them you can see what they mean. Like, let's look at topic 2, for example. You see the words. The words are Iraq, attack, kill, secure, troop, bomb, firefight, things like this. So you can tell intuitively as a human looking at these results from our model that this may be a topic related to like wars, like headlines. Remember, we're using news headlines, so there's a topic for all of this data set can be like war type of or like conflict, international conflict, that type of topic. And then you can see others, right? For example, plan, government, health, labor, service group, change, support. That also kind of gives you an idea of the topic and so on. So very, very nice unsupervised learning here in natural language processing. And now you can also run this model using TFIDF, using those weights that we saw before. So for our LDA multi-core model, when we train it, instead of using the bag of words corpus, we want to use the TFIDF corpus. Pretty much the same thing as before, 10 topics. And now here, and we see here it's actually a little different, because when heavier weights are given to words that are not as frequent, which results in nouns being factored in. So you're taking into account words that may not be that important, like closer. Yes, that may not be very representative. It may be or maybe not, but this actually makes it, for this particular problem of topic model, it makes it harder to figure out the categories or figure out the topics. So this goes to show that the models we apply depend on the type of text data that we are dealing with. So let's look at some performance here evaluation. So let's look at our pre-processed docs. Let's look at this 4,310 that we saw before. And let's go ahead and print out some stuff. So we want so for index, score, and sorted, so we want to sort here the outcome of our model. So we have our LDA model, and we're going to pass in our document here. So our bag of words corpus at the document number of 4,310. So we have that entry. We want to pass it into our model and get a prediction out of it, and we want to sort those predictions by score. So we have our score here. So this is the highest probability. So our model is saying that these words here, this collection of words here, this list of words, most likely corresponds to this topic that contains these words right here: Australia, power, test, help, and so on. So again, unsupervised learning, it requires a lot of human judgment. Look at the output and make sense of it. You have to tune hyperparameters. But it's very informative. I mean, it's pretty amazing how a model is able to learn by itself. Like when we look at the output here of our model, that is able to just very nicely group these words together in this relatively simple tutorial. It's able to really group together words that make sense into a topic without having to use labels. We just give it the raw data, and it just learned to find those relationships in the data in this case, and in the words and the sentences and so on. So the highest probability assigned to that particular topic, and then it starts to go down in probability. So again, this last topic has a very low probability. Now we can do the same with the TFIDF model, and see it's actually pretty different here in this case as well. The scores are different and the outputs are different as well. So it depends on the data that you're dealing with, what model you want to use. But generally speaking, for topic modeling, latent Dirichlet allocation, it's very nice and works very well. So if we test our model on unseen document, so for example, let's create a variable here called unseen document, and let's assign it to this string: my favorite sports activities are running and swimming. Let's just see how our model, what topic our model thinks this sentence belongs to, this collection of words. So let's create a bag of words vector here. So we're going to pass in our unseen document here, this variable, into our preprocess, right, which does stemming, lemmatization, tokenization, and so on. So we have that, and then we pass it into our dictionary.document to bag of words method here. So it's going to give us our bag of words vector, and let's just pass it into our model right here. Let's get a prediction out of our model, sorted of course, and let's see what we get. So it's saying for the highest probability here, 42% approximately probability for this particular topic that contains these words: report, school, expect, time. So that's very interesting. So report, school, time, expect. This looks like it might be like a school related type of topic. And my favorite sports activities are running and swimming. It doesn't seem that far off. I mean, I did give it a 42% probability, but you see the model this is artificial intelligence. It's machine learning. It's able to learn and find patterns. And this is a relatively simple example. I mean, you can imagine a more robust and complex model, and tuning hyperparameters, it can do even better than this. But this is just a pretty amazing example of unsupervised learning in natural language processing using the LDA, latent Dirichlet allocation technique in machine learning. So if you have any questions, thoughts, please comment below, and I will see you next time.